Okay, welcome back everyone. So today we are on our cool programs tab here again, and well, today we are going to be working on some of the other programs. I'm not sure how many we're going to finish, but finish however many we finish today. So let's let's just recap on what we've done. Obviously, these are our imports: pip install SymPy, and here we worked on an AI versus AI rock paper scissors game. Nothing too special here. Pretty basic. Just you could run it if you want. And then over here, we did a prime numbers on a range calculator. We'll just be more specific. Number of prime numbers on a range calculator. You run this, you can go from 1 to 10, maybe you get an output of 4. And that is correct. You can just check that. I'll leave that as an exercise for the reader. Right? Oh, we missed one. Oops. Over here we did a sum of all the numbers. We did a program which takes the sum, which counts the sum of all the numbers which are divisible by the integers 3 and 5 on some interval, which the user can choose. So you can go from 1 to 10. It should be 0. Yep. There are no numbers which are divisible by 3 and 10 and 5. If we go from like 14 to 15, we should get 15, correct? And there we go. And x equals 1 to go into the next term. This shouldn't make a difference. Yeah, okay. Just something to make it more clear. Okay. So again, we just use a for loop and then an if statement, right? Pretty simple stuff. Then we print the total, we initialize the total, all of that. Okay, so let's start off with the parabola x-intercept calculator. So my idea for this is that we define some function. I'll call it quadratic underscore func, right? And we'll take in the variables like let's say A, B, and C, and let's make this user friendly. Let's say we want to allow the user to input something. So integer input. Let's see. So input a value for A. Okay. Right. Then set B equal to, right, input a value for B, and then same thing here. C equals input a value for C. There we go. Okay. And that should compute this here. Right. Okay. Let's just check this. Okay. Now we can just actually set this to be equal to like A1, A2, B1, and C1. Okay. You'll see why later. So define quadratic function here. And my idea for this is that we can just use simply the quadratic formula just to keep things simple, right? We don't have to be too complicated about this, right? It's nothing too crazy. So let's set our sol1 solution 1 equals, we could just call it like x1 equals, okay, so, well, we probably all memorized the quadratic formula by now. Let's see, so we have negative b plus, and we'll just take the first case, so negative b plus math dot square root of b squared pow b2, okay, b squared minus 4ac, okay. And just to make this a little cleaner, we'll just set d equals for AC, and then we'll keep D in here, right? That should simplify things and make it easier to read. Okay. Plus y squared minus 4ac, and then all over that, just, right, let's just check this again. So, math.square root all over 2 times a, right, b squared minus 4ac, okay. X2 can just equal negative b minus, in this case, minus math dot square, let me just copy this. Okay, so we just need to switch this to minus sign. Let's just look at this. Should all be alright. Okay. And then we can just return our value of x1 and x2, so x1 and x2, right? That should all be fine. So input a value of a here. And let's just work from this cell then. Or I'd like to add another cell here. Okay. So basically we just want to print, we just want to set our solution equals, or let's see, so print, we'll just write x equals, comma, let's see, so just quadratic function, so quadratic func, does not make any spelling errors, those are quite common, of A1, B1, C1, and you know that should work. So we can try it out. Okay, I'm gonna run this now. Oh, we're getting that glitch, aren't we? Okay, that glitch that we had in the last episode. Oops, I accidentally pressed reconnect. That's probably not good. Kernel, restart. Okay, go up to the top. Just run that. Let's hope, yeah, there we go. Okay. So parabola, x-intercept calculator. Run this. Okay, put a value for a. I'll just do coefficients of x squared, x, and the constant that I know. So we have 5 and then minus 6. So this should return, well, let's see, so we have x squared plus 5x minus 6x. We can factor that as x minus 1, x plus 6. So we should get 1 and minus 6. As well, we have to print this first, of course. So run that. 1 minus 6, there we go. So that is our solution set, and it seems to have worked quite well. And we could possibly get rid of that again. Get rid of that space. So 1, 5, minus 6. And run that. Yeah, that's fine. It shouldn't be that big of an issue. Let's try again. 1, 5, minus 6. Okay, well, oh well. This still works quite well. Let's just try another one just to make sure. So 1, and let's say, I don't know, 5, and let's see, so 5 to, let's say 6, should give us minus 2, minus 3. Yep, okay, there we go. So that is our quadratic x-intercept calculator finished. Okay, so now let's go on to systems of equations calculator. In this case, a system of 3 equations. So let's see, so let's define a function, matrix, we'll call it matrix 3. and we'll take in the variables A, B, C, D, E, F, bear with me here, G, H, I, and then sol, and then equal 1, equal 2, equal 3. And basically I'm taking all this information because, you know, in systems of equations, we essentially have three equations where we have three variables or obviously three algebraic equations, and we have three variables that are scaled in some way on one side and one constant on the other side. Usually you might have to make some transformations and there might be like other values over here, but that's besides the point here. We don't have to worry about that right now. So it takes in these values, right? And we're actually going to use some new functions here. So np.array, we have A, B, C. So this just makes sure it looks like a 3x3 matrix. So D, E, F. And if you don't know much linear algebra, then this probably won't make much sense to you. I'm assuming that you know a bit about matrices. G, H, I. So that's going to be our A. And just for some context, I've talked about this before, but let's just go to JS Paint. Okay. And basically, if we have some matrix A, in this case, this is going to be the one that we're working with right now. So we have A, B, C, D, E, F. And you see why I use the array function. We have A, B, C, D, E, F, G, H, I, right? And essentially we use this matrix product here by x, y, and z. These are our three variables since it's a system of three equations. And this is equal to, well, whatever is over here. So in this case it's our equal 1, equal 2, and equal 3. Okay, and essentially how this multiplication works is you go here. So the row information on this matrix applies to the column information on the second matrix here. So essentially we just have AX plus BY plus CZ equal 1, and then we have dx. That's obviously our first equation here. So then we have our dx plus ey plus fz equals 2, and you get the idea for the third one, right? And essentially, how do I say this? As convention, usually people name this the matrix A, and of course it's bolded. And then the matrix X, at least I do, and then equals B. So X and B in this case are our vectors, right? They're column vectors. So this is what we're working with here. Okay, and essentially to solve for X in this case, which is what we want to solve for, we just multiply by A inverse on both sides. And actually, matrix multiplication is not commutative, so we have to multiply on the same side, right? So let's do that. And this goes to the identity matrix, the identity matrix is just 1, 1, 1 all the way, and zeros, zeros, you know, you get the idea, zeros, so it's all zeros. This applies to square matrices, okay? So, okay. So that's the basic idea of what we're doing here. And let me just make this clear. So our final solution is just going to be equal to, or well, we'll write it as our x. Oops. Control Z is our friend. Okay. Okay, so final x is equal to, and the identity matrix multiplied by any other matrix is just that matrix. It's commutative as well in this case. So A inverse multiplied by B. That is our solution. And that is what our program will solve for. Okay? Cool programs. Okay, and then our matrix B, as we saw there, is just np.array. Well, it's just going to be equal 1, equal 1, right? And then equal 2, and then equal 3. Except this is a matrix here. Alright. And then basically our x is just going to be equal to, I think this is the command, np.solve. Not actually sure. We can quickly check though. And then we just want to return our x here. We can quickly check if we run this. So print. We'll do this on a separate module here. See if we get any errors. Oh, it doesn't look like we get errors, but maybe if we, yeah, we still might get an error. But let's check. Okay, everything should be correct. So let's print out our matrix. So matrix, or let's just call our function. So we'll just set some arbitrary values. And again, it might not function actually because sometimes the solution might be imaginary, or and that normally translates to a function or a, in this case our a, not which our a that doesn't have a, you know, get it, a, that would normally mean that our a doesn't have an inverse, okay? So it can't be inverted, and that is possible because sometimes the determinant is equal to 0, and you don't want that because then you get 1 over 0 in the formula. So, oh, how many have I done? Okay. Okay. 2, 4, and then 12, 14, minus 10. This is very random, by the way. So this should be it. So we should have 12 terms, right? So that's 3, 6, 9, 12. Okay. So let's try this out. Oh, attribute error. Yep, as I suspected. You know, I prepared for this. np.lin. Okay, got it. I remember now. Lin algebra, in your algebra solve. Okay, let's run that again. And there's our fairly complicated solution. So there we go. But nevertheless, this is our solution set. And actually, it's peculiarly enough the way computers interpret this. Basically, this is our z value, this is our y value, and this is our x value here. So just for some context, but nevertheless it does function. And we can make this user-friendly by making these all input values, but I couldn't be bothered to do that right now. So let's move on to our last one for today. Of course, we'll work on these later, and since they require a little bit more work. So derivative calculator, and using the definition. Okay, so this doesn't require any imports, it's just some basic approximation to the derivative of a function. So let's define a function to be taken, so basically to be derived here. In this case, to be taken the derivative of, and basically we'll just have this in terms of x, right? Okay. And we'll return x squared. We'll just call this g of x because it's more simple, right? We'll just call it g of x, and then return x squared, okay? And then we'll define another function, which is the derivative, and it's in terms of x. Okay, and so basically, this might be a bit confusing if you don't know the definition, but we'll just work through this, okay? So we know that slope is rise over run, or just like the difference in y value over the difference in x value. Okay, so first let's set some variables. So our h in this case is basically our, so we have our, we can go back to the JS Paint here, get rid of all of this. So essentially, let's look at the graph here. It's kind of hard to explain if we don't have a graph. Okay, so here we have a coordinate here, here we have another coordinate, okay, we have some tuples. Let's say this is some point x, this is x plus h, and this is obviously f of x, and then f of x plus h, right? And obviously we're going with x squared, so we have that, and then that, this point, oh whoops, what am I doing? Obviously I didn't do this very well. Okay, that's going to be somewhere up here. This is obviously not to scale, definitely not to scale, but we have some function here. Okay. We'll just write this here, right, and then, this is closer, right, okay, there we go, this is the coordinate x plus h, oops, yeah, x plus h, f of x plus h, okay, and then this is the coordinate x, obviously, then f of x standard, right, and we want to find an approximated slope here. That would be this here, this line, tangent line, or the secant line between these 2 points. And our end goal is to find the tangent line, or something very close to the tangent line, since we're not using any imported packages. And how we want to find that is we want to divide this value here, we'll call it dy, and divide that by dx, right? And our dy is just equal to, well, it's just equal to f of x plus h minus f of x, right? And of course our dx is just, well, this value minus this value. So cancel the x, we're left with h, so dx equals h, okay? And obviously we're not using limits, so we want our h to be some number that's closer and closer to 0, so we want a larger and larger denominator. I mean, yeah, here. And we'll keep it all zeros just to make it simple. Okay? And then and that's basically the entire idea. And finally, then we want to actually plug this in. So finally we get f of x plus h minus f of x over h. And normally you would see the limit as h approaches 0, but in this case we have h getting closer and closer to 0 like this, since, like I said, we're not working with limits right now. Okay, so mamaya robię wideo.
Go!
Ja robię wideo.
We can send you here.
Mama, ja robię wideo. Sorry about that. Okay. Oh well. My mom came into the room. Okay. Let's write it clearly. And yes, this will get closer and closer to a tangent line. And that's the idea. So this is just dy over dx, and this is the derivative. Approximated derivative. So let's try doing this. So, let's get started. Okay, so we want to set, well, in this case, our dy was f of x plus h minus f of x, and let's set our h here beforehand. So our h is equal to, and we'll let the user choose this, so number, and let's try this. So number equals integer input input a value for h. Okay. So that's very simple. And of course our dx equals h. So we don't even have to worry about that. We'll just keep it there for clarity. And finally our slope, we'll set a new variable here. Slope is equal to dy over dx, right? And finally we can just return our slope. And that should be functioning value. And of course we're taking the derivative at points on the graph of x squared. Okay, you can change this up if you want. Trigonometric functions most likely wouldn't function in this case. You could try that. So put a value for h. Oh well, actually this is not going to work, since obviously we need to derive it at a certain point, right? You can actually work with partial derivatives later on. So let's do it at it's 5, and that should be the value that it should spit out should be quite close to 10. So we can check that. So the larger the number here, the better. We'll do like 10,000. Oh, we have to run this again, don't we? Yep. Okay, 10,000. Oh, what's our error? Name f is not defined. Oh, I see. We used g of x instead. I just forgot. I'm just so used to f in this case. So let's run this again. Let's go 10,000. And that's yeah, that's quite close to 10. As you can see, it's very close to 10. So quite good. We can try different values. And this is what I find quite cool about this. So let's go again. Obviously it's getting closer and closer to 10. Again, I'm not sure why I chose 5 again. So again, we can just input a value here. Input a x value. Okay. So run this. Input a value for h. put in an x value. Okay, I'll like do maybe some arbitrary value 7. And yep, it's close to 14. Obviously the derivative of x squared is 2x. Use the power rule and plug in 7, we get 14. And well, pretty much I think that's pretty good for now. So hopefully you enjoyed the video, and I'll see you in our future videos. Obviously this is still only part 2. So have a nice day. Goodbye. Oh, and don't worry, we'll continue our series on Taylor polynomials and or Taylor series. So have a nice day, and goodbye.